I am planning on grading your tests and your assignment, computational assignment today. So stay tuned for that. You'll see your score on Learning Suite, and then if you want to come pick up your exam from my office, you can, or I'll just bring them next time. I'll let you know when I've completed grading them. Let's see, anything else? All right, so we've been talking about conformations of molecules. We've been talking about strain. We were moving ahead to sort of electronic factors, and I realized there was an important steric factor that we hadn't talked about yet, but that is reasonably important. So you'll hear people talk about this as the gem dimethyl effect. Gem means on the same carbon. Geminal, it comes from the Greek word for twin, Gemini. And it's also, if you like reciting the names of dead people who discovered stuff, it's sometimes called the Thorpe-Ingold effect. So if you want to use that, most people will maybe not know what you're talking about, but they'll assume you do because you know the names of those guys. And this is related to the idea that when you have two methyl or two alkyl groups on the same carbon, there's some unique things that happen. So as an example, here is a phenol, and it's got a carboxylic acid. And under certain conditions, which we won't worry about, you can cyclize to form the six-membered ring lactone. Oops, I guess my six-membered rings need a little bit of work. Yeah, we pressed record. And a lactone is a word for a cyclic ester. If you've not heard that before, that's sort of what we call them. If it were an amide, we'd call it a lactam instead of a lactone. And they compared the rate of making this lactone with rates of other molecules where they started to incorporate methyl groups. So we'll call the relative rate here 1. That's just our control molecule. Then if we place two methyl groups in the carbon chain that bears the carboxylic acid, if we put them right there, the rate of making the lactone goes up by 4,500. So that's pretty dramatic. Sometimes in physical organic chemistry, when you see an effect, you try to push it and see how far it can go. And so this is actually, I looked this up, this is from the Wikipedia page. If you try to add methyl groups to the aromatic ring, they're far enough away from the carbon chain of the carboxylic acid that it doesn't make much of a difference. It basically has the same rate of making the lactone, but if you combine those methyl groups on the ring with the methyl groups on the carbon chain, suddenly the rate of making the lactone goes up by a factor of 100 billion. So what's going on there? It's thought that this has to do with something called steric compression. So let's just imagine a group that doesn't, let's imagine the bond angle between two groups on a carbon where there aren't two other methyl groups. Basically, we're comparing bond angles in a secondary versus a quaternary carbon. Okay, and you know, who knows what the bond angle here will be. It will be affected somewhat by the fact that you've got two R groups here and two hydrogens here. So it may be somewhat larger than 109 degrees, maybe just because of sterics. But when you replace these methyl groups with these hydrogens with methyl groups, suddenly the methyl groups are repelling each other. That's causing them to push away from each other like this, which in turn is going to compress these R groups toward each other. So if we measure angle theta, I'm not sure, we'll call this angle theta 1 versus angle theta 2, what you see is that theta 2 is smaller than theta 1. Having those two methyl groups compresses this bond angle, and you put them a little closer together, and that can accelerate reactions. Questions about that? So the reason I bring this up is because you'll see it in a number of places, and if you ever see somebody putting two methyl groups on a carbon, you'll know what they're trying to do. They're trying to make cyclization happen more effectively, or trying to bring two groups closer to each other. A classic example of this is the amino acid AIB, amino isobutyric acid. This has two methyl groups on the alpha carbon instead of just one. So this is in regular amino acids like alanine, there would be a proton here and a methyl group there. For amino isobutyric acid, or AIB, there's two methyl groups. And this does some interesting things to the dihedral angles phi and psi. We don't, we could draw those out if you wanted to. It's not necessarily that important for the discussion, but this same gem dimethyl effect acts to constrain phi and psi to values near minus 57 and minus 47. Remember, those are the preferred dihedral angles for alpha helices. So sometimes when people want to make peptides, particularly short peptides, and they want them to adopt alpha helices, they'll incorporate a number of these AIB residues to promote that. These angle values are maybe not precise, and there's with very short peptides, this promotes an alternative helical conformation called the 310 helix, but that's not important for our discussion today. But you can use this kind of thing to promote certain kinds of structure. And it's sort of an example of the kind of pre-organization thing I was talking about in the seminar yesterday. You do things to make conformations you don't want less favorable. All right. So any questions you want to ask about that? Another way people will talk about amino acids that are like AIB, they'll call them alpha-alpha disubstituted because they have two non-hydrogen things on the alpha carbon. All right, so we were talking about something called the Gauche effect, and I was pointing out that in spite of what you might think for 1,2-difluoroethane, the anti-conformation, where the two fluoro groups are anti to each other, is actually less stable than the conformation where the two fluoro groups are gauche to each other. And this goes against what you would predict from sterics. Fluoro is just a little bit bigger than proton, not by a lot, but you would have predicted based on sterics for this effect to dominate. Nevertheless, this one is more stable. And we were thinking about the answer why. And in order to do this, we need to review a concept from valence bond theory, but we're also going to consider MO theory as well. We're going to use a hybrid approach. And we're going to talk about what are called sometimes donor-acceptor interactions. That's interactions between a filled orbital in the molecule at one location and an empty orbital in another location. Sometimes it's called hyperconjugation. Of course, in pure MO theory, there's no need for any such thing because all of the orbitals are delocalized anyway. MO theory sort of accounts for that in the basic math of how it works. But it's helpful in sort of thinking about these issues to take a hybrid approach. So when we think of, excuse me, 1,2-difluoroethane, we're going to consider the sigma bonds as being 2 electrons shared between 2 atoms. Okay. And now let's consider where we would expect in energy the sigma bonding orbitals to be versus the sigma star anti-bonding orbitals to be in energy, just relative to each other. All right. We've got a few different kinds of bonds. We've got 4 carbon-hydrogen bonds. And then we have 2, I don't know why I can't count. We have 2 carbon-fluorine sigma bonds. Also, we have a carbon-carbon bond, but that's the one we're not involving that at all in this process other than it's the bond we're rotating around. And of course, if we have 4 carbon-hydrogen sigma bonding orbitals, we should have 4 carbon-hydrogen sigma star anti-bonding orbitals and 2 carbon-fluorine sigma star anti-bonding orbitals. Just for the sake of our discussion, if we're thinking about a carbon-hydrogen bonding orbital, that would presumably come from an sp3 type orbital on carbon overlapping with a 1s orbital from hydrogen. And if this is carbon and this is the hydrogen, that orbital is going to look something like this. Similarly, if we were to overlap an sp3 orbital on carbon, probably with the corresponding p orbital on fluorine, we would expect a bonding orbital that looked like this with a lobe between the 2 nuclei and then lobes on either side with the other face. Anti-bonding orbitals, so those would be sigmas. Anti-bonding orbitals would presumably look like this. For carbon and hydrogen, you would have a node in between the 2 nuclei and then a smaller lobe here and a larger lobe there, and then a lobe there, and we'll just use shading. This is the minus combination. Similarly, the sigma star for the carbon-fluorine bond would look like this. Large lobe in this direction, small lobe here, node there, small lobe there, large lobe in this direction. So what I've drawn for you here are localized bonding and anti-bonding orbitals. This is what you would get if you did Gaussian and you clicked the box that said NBO analysis. This is a version of molecular orbital theory where you mathematically transform the molecular orbitals into localized orbitals, and the way of describing the molecules are fully equivalent. Any questions about what sigma and sigma stars look like? Okay. Now, let's talk about their relative energies. Okay, and we were doing this just as class ended last time. Carbon-hydrogen bonds are generally worth, their bond association energies are about 104 kilocalories per mole. In contrast, carbon-fluorine bonds are worth about 109 kilocalories per mole. So, if you have to rank in energy where sigma bonding orbital should be, where is the carbon-fluorine bonding orbital relative to the carbon-hydrogen bonding orbital? Should be lower, right? And you can tell that just from the bond energy. But if we wanted to rationalize that, what we would say is that when you make a bonding orbital between an sp3 hybridized orbital on carbon and a 1s orbital on hydrogen, you get the sigma bonding orbital here. But fluorine starts out at a lower energy level. The 2p orbital on fluorine is actually lower in energy than on the orbital on hydrogen. Fluorine's more electronegative than hydrogen. So this means that because you start out at a lower point, the bonding orbital you make is going to be lower. Okay? Now, how about the energy difference between the anti-bonding orbitals, sigma star for carbon hydrogen versus sigma star for carbon fluorine? What do you expect there? Do you remember what we learned in, what was it, chapter 14 or chapter 1? When two orbitals are close in energy, the amount of stabilization relative to the starting orbital is higher, and the amount of destabilization relative to the starting orbitals is also higher. Whereas when two orbitals are different in energy, the amount you go down relative to the starting orbital is smaller. Now, you started out lower to begin with, so the orbital that you make is still lower in energy than the carbon-hydrogen bond. But what this means is the sigma star antibonding orbital for the carbon-fluorine bond isn't going to be as high above carbon as the sigma CH antibonding orbital is. In other words, another way of thinking about this is just to start with the carbon-hydrogen sigma and sigma stars and then say, let's switch hydrogen to fluorine. Fluorine's more electronegative than hydrogen, so that should pull both orbitals downward. That's an alternative way of thinking about that. It's called perturbation theory. Yeah?
So before we learned that the anti-bonding orbital is always more destabilized than the bonding is stabilized?
Yes.
Does that not apply here then?
You're exactly right, and that just means that my drawing is dumb because I didn't do it to scale.
Okay,
So, shall we try again?
No, it's okay. I just...
Yeah, so here would be an sp3 on carbon, and let's say a 1s on hydrogen. So here we've gone down in stability by about 3 units. Here we've gone up about 4 in our drawing. This would be the carbon hydrogen sigma star. This would be the carbon hydrogen sigma. Let's say fluorine starts out here, and I don't, relatively, I'm not sure how that would go. Let's suppose we only go down 2 units for fluorine instead of 3. Because the difference in energy to begin with is larger. But by virtue of the fact that fluorine starts out lower, even though we're only stabilizing by about 2 units, we're still lower in energy than the carbon hydrogen sigma star. Then let's say the anti-bonding orbital will go up by 2.5 or 3 units. That's still larger than the little red line here, but it doesn't put us as high above carbon as we were for the carbon-hydrogen orbital. I think that's maybe self-consistent. But it's also fine if you don't want to go through all of that to just say, okay, well, here's where carbon-hydrogen sigma and sigma star are. Replacing hydrogen with fluorine, which is more electronegative, pulls both of those down in energy. So what that means is that my highest, and of course the carbon-hydrogen bonding orbitals would be filled, the anti-bonding orbitals would be unfilled, but my highest energy bonding orbital is going to be sigma CH, but my lowest energy anti-bonding orbital is going to be the carbon fluorine sigma star. Now, how does that play out in the conformations of this molecule? One of the things that we didn't talk about when we were discussing staggered versus eclipsed, and in particular when you were doing those MO calculations, is that the staggered conformation allows a sigma bonding orbital that is filled on one of the carbons to overlap with a sigma star antibonding orbital on the adjacent carbon. Now you can go through this analysis using group orbitals and you'll get the same answer, but this is a useful way of thinking about it. Imagine you have a filled orbital in the same molecule as an adjacent empty orbital, sigma star carbon-hydrogen bond. The filled carbon-hydrogen bond can donate electron density into the antibonding orbital. That's called hyperconjugation. You can think of this as though there was some orbital mixing going on. So imagine having a carbon-hydrogen bonding orbital mixing with a carbon-hydrogen sigma star antibonding orbital. The bonding orbital is going to go down in energy just a little bit. The antibonding orbital is going to go up in energy just a little bit, but we don't care because the electrons delocalize a little bit and they go down in energy. That's a stabilizing effect. If you can't see how these line up, consider drawing a Newman projection from this angle and convince yourself that this bond, a bonding orbital, lines up with the large lobe on the carbon-hydrogen antibonding orbital on the adjacent carbon. So that's, in addition to sterics, that's one factor, one reason why staggered is more favorable than eclipsed. Now, let's replace both of those hydrogens with fluorines, shall we? And see what happens. And see if there's an alternative, better arrangement. So, imagine we start in the anti-conformation, which I've already told you is not as stable. Let's draw the carbon-fluorine sigma bonding orbital. And we'll do this with sort of a large lobe here, smaller lobes on the outside, and have this be pink. Nodes at the nuclei, wave function change in sign. Colors simply represent opposite wave function signs. Let's draw the antibonding orbital for the carbon-fluorine bond. As we would expect, there would be a node in the middle, small lobe here, large lobe there, small lobe here, large lobe there. We can fill in the colors representing wave function sign. Here you have a filled carbon-fluorine bonding orbital and an empty carbon-fluorine sigma star. And you could still get donation of electron density from the carbon-fluorine sigma to the carbon-fluorine sigma star. But let's consider an alternative. What if we keep everything the same, only we rotate around the bond between carbons 1 and 2, such that instead of having a fluoro anti to the other fluoro, we now have a hydrogen. Okay? In that conformation, the empty antibonding orbital that would line up with this filled carbon-fluorine sigma bonding orbital would no longer be the carbon-fluorine sigma star. Rather, it would be the carbon-hydrogen sigma star. Now, based on what we've talked about, which of these arrangements is better? Is it better for the carbon fluorine sigma bonding orbital to overlap with carbon fluorine sigma star or carbon hydrogen sigma star? What do you think?
Probably
Carbon hydrogen, right? Okay, can you explain why?
because you told us it was more stable.
Because I told you it was more stable. Good.
Maybe because of hyperconjugation, as you explained earlier.
Because it's because of hyperconjugation, but that's going on in both of these cases. So do you have any reason to believe this would be better than this? This hyperconjugation would be better than that one? Go ahead.
There's less nodes.
Okay, fewer nodes. I will agree that the hydrogen doesn't have a node there. That will. Does that have a major effect? I don't think that's the major thing that's going on. Let's just compare two options. Carbon fluorine sigma bonding orbital gonna mix with either a carbon. Did I go about this the wrong way? Oh, I am thinking of this backwards, aren't I? Okay, I need to back up just a little bit because where we're going, we could come around to the right answer. But the real deal has to do not with the reason for this has to do not with which orbital the carbon fluorine bond is donating into, but rather with, why is this not working in my head? Just a second.
I think from the orbital diagram we drew, the carbon fluorine is closer to the carbon fluorine sigma bond is closer to carbon fluorine antibonding orbital.
Okay. So let's frame the discussion this way. I'm going to erase what I've drawn over here on the right because that wasn't the right comparison to make to help you see the stability difference. Of the two empty orbitals that we have, which is going to be the best acceptor? The lower energy one, right? The carbon fluorine sigma star. Of the filled orbitals, which is going to be the best donor? Carbon hydrogen, right? So what I really should have showed you is compared the situation. Here is our best carbon fluorine sigma star. This is our best acceptor. What I should have compared is having our carbon fluorine versus carbon hydrogen donating into that best acceptor. So I'm sorry for that oversight. Let's leave the carbon fluorine bond over here in that place, and let's continue to draw that carbon fluorine sigma star right there. But instead of having the carbon fluorine bond being the donor, let's now have the carbon hydrogen bond being the donor. And what I hope you'll see is that having the carbon hydrogen bond anti to the carbon fluorine bond lines up our best, Joshua, our best acceptor with our best donor. Okay. Do you see that? It's only when the fluorine is anti to a hydrogen, that you line up your highest energy bonding orbital, which is the carbon-hydrogen one, with your lowest energy anti-bonding orbital. And it just so happens that when you do that, doesn't matter whether it's this hydrogen or we rotate that hydrogen, the fluorines are going to be gauche to each other. Okay? That's called the Gauche effect. When you have electronegative heteroatoms on adjacent carbons, they might prefer to be, there'll be a preference for them to be gauche with each other. Yeah?
Okay, so I was doing a question with my organic students, and we were talking about basically this, and they were drawing Newman projections with it, and we decided that the more stable was the gauche. That was the major product, and they said it was because of the dipole moment.
Okay, because of the dipole moment.
Between the two fluorines, and the other one would have a net dipole of 0, and the compound has a net dipole, I think it was like 2.5.
Right, so...
is that just a result of this, basically?
Well, so the way of reasoning this out was that over here, the dipole would equal 0. Over here, there would be a net dipole. Is that right?
Yeah.
Okay, so my question back is, well, which of those is more favorable, and how can you tell?
Yes, that's what I'm asking.
Okay.
I'm saying, do we know that this one, like the question was like, this is more favorable because it has a net dipole moment. Is it really more favorable because of this effect that we're learning right now?
I think so. I think so. The dipole thing should be a consequence. Now, we're just imagining these molecules by themselves, right?
Yeah.
I would think that alone in the gas phase, probably having a 0 dipole is maybe better. But can you think of a situation where having a net dipole might be better? What if you're not in a vacuum? What kind of solvent might promote having a dipole? Polar, right? If the solvent is polar and has dipoles, then maybe the conformation that has a dipole is more favorable. So I think it's context dependent.
Okay.
But all other things being equal, there's some bias in favor of gauche. And I think you're right. I think the net dipole thing may be a consequence of this effect, not the reason for it.
Okay.
Yeah. Others?
Oh, I have another question,
Yeah.
sorry. I guess I was just kind of confused about why we're comparing, because usually we just compare like filled to filled and antibonding to antibonding.
Yeah.
Are we just comparing the filled to empty because of this difference where our highest energy bonding is the sigma CH and our lowest antibonding is the sigma
Right.
CF?
So the reason we're doing that, if we were doing MO theory, what we would have done is we would have taken the two basically methyl groups, and we would have distorted them by substituting one for fluorine, and we would have had to see how that changed the methyl groups. Then we would have brought the two methyl groups together, and we would have considered whether it would have been better to have the fluoros gauche or anti to each other. And we would have seen that in some cases there's better orbital overlap, or there's more stabilization because of two orbitals mixing at the same energy versus different energies. And that would have led us to this conclusion. That's difficult to do in your head, so treating each bond as an individual sigma bonding orbital with an associated sigma star, but then considering the ability of filled and empty orbitals to mix, takes valence bond theory and mixes in a little bit of delocalization so you can get to the answers of MO theory. Yeah. Okay, others? So this can have some interesting consequences, and this is what I wish maybe I had my notes for. Can I remember it? Maybe I have to go peek at the last year's notes so that I make sure that I don't get this wrong. Professor Ronald Rains used to be at the University of Wisconsin-Madison when I was there, and he is now at MIT, and he's done a lot of work with the amino acid proline. Why can't I see things? And understanding conformations within proline. So I just need a quick glimpse of this will be enough. And one of the reasons he's interested in proline is because by far the most abundant protein in your body is collagen, and collagen's made up of tons of proline. But in addition to regular proline, collagen is also made up of hydroxyproline. So here's the amino acid proline. It's kind of weird because you have a secondary amine. So here's the nitrogen, here's the alpha carbon, and here's the carbonyl carbon. And notice that in the case of proline, the side chain and the amine are linked together. You might expect this ring to constrain, in particular, the phi angle because you can't adopt all possible phi angles because you can't rotate completely around the bonds in a ring, right? And it does, and there are, it basically constrains phi to have negative values, and it constrains psi to have positive values. But one of the amino acids that's present in proline, in collagen, is not just proline, but actually the body post-translationally modifies proline to have an OH group there. That's called hydroxyproline. And actually, even though we think of the 20 natural amino acids, what we really mean is the 20 amino acids that are encoded by tRNAs, because hydroxyproline is present in more abundance than some of the 20 amino acids, which is kind of wild to think about. But Rains did some studies on trying to understand why nature uses hydroxyproline, how that helps. Does it make collagen structure more stable? And the issue really had to do, on one level, with the fact that for proline, because the nitrogen is attached to two different carbon groups, you have a choice in terms of rotation around the omega bond. Do you remember how I told you that omega dihedral angle was boring because it's either 0 or 180, and most of the time it's 180? Well, proline is the exception to that. So I'm going to redraw proline, and we'll put the nitrogen here, and we'll put the next carbon, the next carbonyl carbon there, and then here is that one. So this is the phi angle, this is the psi angle, this is omega. In a normal amino acid, let's have this be an R group, this be the carbonyl carbon, and this is the carbonyl carbon of the previous amino acid. In a regular amino acid, it's, if you look around, if you look down the bond between the carbonyl carbon of the previous amino acid and the nitrogen, it is best to have this bond and that bond anti to each other. Does that make sense? In that case, the dihedral angle would be 180. But the reason that is the case is because it's better for the bond on the carbonyl carbon to overlap with the smaller NH bond. But if you replace that NH bond with another nitrogen carbon bond, there isn't as much of a difference anymore. So for proline, proline exists in an equilibrium between having the trans amide conformation, that is 180 degrees about this omega bond, or having it in the cis conformation where the carbon group on the carbonyl group is on the same side of the amide bond as the alpha carbon. It took me forever to figure out what the heck people were talking about when dealing with cis and trans amides. So let's go through that one more time. Amide bonds are planar. We're going to pretend they're like double bonds. The trans double bond is what you call a double bond when the group on one side is opposite to the carbon group on one side is opposite to the carbon group on the other side, right? Now, do you remember how with alkenes, once you go tri-substituted or more, we drop the cis and trans because you have to worry about who's cis to what, and so we just go with E or Z. We can do that with amides too, but we're lazy and we don't. So let's just say the group that we care about in terms of assigning cis versus trans on the nitrogen side is always the alpha carbon. And so what we're really asking, and this is the carbonyl carbon and the alpha carbon to the previous residue, is are the alpha carbons on the same side of that amide bond or on opposite sides? If they're on opposite sides, it's trans. If they're on the same side, it's cis. Okay? Normally, and we could draw the cis conformation, I guess, for a regular amino acid, but normally that hold up. Sorry. Normally, the cis conformation around the amide bond would be unfavorable because of sterics. Right? You'd have the alpha carbon eclipsed with the other alpha carbon. But in the case of proline, either way, you're eclipsed with a CH2 group, so who cares? All right. And it turns out that one of these two conformations is better for collagen structure than the other is. Turns out that for proline, if you have it in the trans conformation, that's best for fitting into collagen. Okay, so you would predict that nature would do some things that might bias the molecule towards having a trans amide conformation. Okay. Now, there's another wrinkle to the story that we need to talk about. This one you'll have to maybe just accept, and then we'll get to the influence of the Gauche effect. If we draw proline sort of from the side, here's the nitrogen, and let's show the proline ring in one of two possible five-membered ring envelope type conformations. So if it's okay, I'm going to switch to this model compound that's easier. This is a carbonyl carbon, but instead of having it be in a peptide with a squiggly mark here to represent everything else, we're just going to use the methyl ester. And on this side, instead of having another amino acid, we're just going to use an acetyl group. And this is a fairly reasonable model compound for dealing with proline. Here's the carbonyl carbon. Here's the alpha carbon. Here's the nitrogen, and here is the beta carbon of the side chain. And what I'm going to draw for you, let's see, is the so-called envelope conformation, where I'm really bad at this. Looks something like this. So alpha carbon, beta, gamma, delta. Alpha, beta, gamma, and delta. That's gross. And in the particular conformation that we've drawn, the gamma carbon is sort of pointing down out of the plane that's sort of established by carbons A, B, and C. I'm sorry, nitrogen, alpha carbon, and beta carbon. We call this the C gamma endo. Oh, sorry. Why do they call it C gamma exo versus endo? I don't know. They call it C gamma because we're dealing with whether this gamma carbon is pointed up versus down. Why it's exo versus endo, I got nothing. But there's an alternative conformation. We would call this the C gamma endo pucker, and that's where that gamma carbon is elevated out of the plane of the ring. So let's draw it again. Here's the methyl ester with our carbonyl carbon. Here's our alpha carbon. Proton here coming out at us is this nitrogen that's bonded to an acetyl group. Here's the beta carbon. In the gamma pucker, the gamma carbon's going to be up like this. And the delta carbon is going to be down like this. So it's about whether we swing this gamma carbon up versus down. All right. And it just so happens that the endo conformation, it just so happens that the exo conformation for some reason favors having the two alpha carbons trans to each other, whereas the endo conformation favors having those two carbons cis to each other. And this is just based on studies of I think, of proteins that have proline in them and just analyzing them. And when you have cis amide bonds, the ring tends to have a C gamma endo pucker. When you have trans amide bonds with proline, the ring tends to have a C gamma exo pucker. All right. Convoluted, I know. But the story is actually interesting because so you would want, if you wanted to make a more stable collagen where you need trans amides, you would want to somehow bias the ring to be in a C gamma exo conformation. Could you do something that would make that possible? And the answer is yes, of course. And if you look at hydroxyproline, what hydroxyproline does is it puts an OH group on the gamma carbon at a down position. And if you were to look down this bond between gamma and delta carbons, and I'll take you through this in a little bit more detail when we're back on Monday. Here's the beta carbon nitrogens. Let's see, delta carbons in the back. Nitrogens here. Notice that when we're in this C gamma exo conformation, the two heteroatoms are gauche to each other. So nature somehow discovered long before we did that putting an OH group down at that location favored the C gamma exo conformation because the two heteroatoms on adjacent carbons would be gauche to each other, and the Gauche effect would promote that. So if you have the hydroxyl group here, you favor the C gamma exo, and you favor, therefore, the trans orientation of that amide bond, and that makes your collagen more stable. In contrast, and we'll go through this next time, we'll show you that if we were to, in the C gamma endo conformation, the OH group would actually be anti to the ring nitrogen, and so you don't have that beneficial effect. Raines has taken this discovery, made lots of mileage out of it, tons of papers about it, tons of interesting things where they biased the ring towards one of these conformations or the other and put them at different positions in collagen. We don't have a lot of time to go through all of that, but it's some interesting literature to read if you want to get into it. We'll review this a little bit on Monday, and then we'll move on. So have a good weekend. I know I'm behind on posting notes and videos. I'll catch up on that today.